So today I want to go over a basic example of actually using concurrency in Go outside of just a very basic example, a way that kind of illustrates how you would use it in the real world. So to illustrate this, I created this data.csv via this basic generate function. Essentially all it's doing is it's just generating integers between 0 and 10, and then it's putting them into a multidimensional array of 1000 by 10,000. So it's got this gigantic array, and all this program's going to do is it's going to sum over all of those arrays and get the sum of everything that was generated. So this is a pretty basic trivial program that you could do without concurrency. Now the issue that you're going to have there is that you're going to be going over each and iterating over every single line in every single dimension, and it's going to be really, really slow because those are going to be blocking. So I implemented that in this with concurrency method. Without concurrency. So I implemented that here. It's very simple. All you do is you just read in the file, you go line by line, and then you call this sum method, which simply reads in the line, and then it will split it up by the comma, parse the integer, and then add it to a sum and return it. Not the most efficient or fancy thing in the world, but it illustrates this pretty well. So all the without concurrency is going to do is it's just going to go sequentially. It's going to block every single time here. So it'll go over each line, wait for it to sum. Once it's summed, get the next line, so on and so forth, the way any normal sequential program would work. Now what I want to look at is how you would do this with concurrency and what this and the concepts that I used. So the two big things I used were wait groups and channels. So inside here, it starts about the same by reading in the file, but then where it gets weird is right here when I declare this wait group and this channel. So for those who aren't familiar, what the wait group is effectively a way for you to block the execution of the method or the thread until a certain condition is met. So the way you do that is by calling wg.wait. So down here in this Go routine, we're waiting for the wait group to finish, and then once the wait group is empty, we can then close C, which is our channel. So, and then the way we can set the wait group is by either incrementing its internal counter or decrementing its internal counter via add or done. So that's pretty simple. And then the channel is a way of passing data and messages in between two different Go routines. So you can think of it as a sender and a receiver, depending on where you put the arrow. So if you put like sum pointing to C, think of that as putting the sum into C. And then if we did, for example, test : equals, and then pulling out of C, we're going to be pulling a value out of C here. So that's pulling it out. So you can either put in or pull out. So then the way I'm actually reading out is a little different. I'm using a for loop to read out of the channel. So channels can be, you can pull stuff out of a channel in a loop, which what this loop will do is every time there's something inside the channel, it'll pull it out and it make that element S, and then you can call whatever you want on that. It'll keep running this until the channel is both empty and closed. And we're closing the channel here, and then it'll be empty once it's gone through and summed everything that we put inside of it in this Go routine. So it's the same idea going line by line. It's just that every time we want to sum an individual line, that is a concurrent request that gets spun off via a Go routine, and then we spin off all 1000 of those really, really quickly. And then once they're done, it doesn't matter what order they're done in, they get put into this for loop, added to a total sum. And then once we've done all of those, which means that WG, its internal counter, has been set to 0, this wg.wait will stop blocking, and then it will execute close C. Once C is closed, this for loop will terminate, assuming C is empty. It'll return the sum, and then we're done. So let me go ahead and save this and execute it. And what's cool is I benchmarked it in main, so I just went ahead and I just timed it with the time function, and we can see very clearly that with concurrency, we get 96 milliseconds. Without, we get 182 milliseconds. So there's a very, very clear performance uptick here. Obviously, they get the same number, and we can just keep running this, and you're going to get the same thing over and over again. So it's a slightly different ratio because it's non-deterministic, but you get the idea. So the question then becomes, how is this actually useful? In real life, you're never going to have to, sum over an array like this, and it's not practical. But what this represents is effectively being able to take a collection of n items and do something that takes a long time on each element. A really good example of this would be a table of users, reading out like 1,000 users and then doing a long calculation to each one, maybe going through and checking their billing history and adding something to them or whatever. You can spin off 1,000 concurrent processes for each of those users, so each one gets their own thread and they can execute at the same time effectively instead of having to wait for each user to do their things. And especially if you're calling an external API or database that could take a long time, it's really, really useful to be able to do all that concurrently so that you don't have to wait and eat the cost of waiting for everything. You don't just block your thread and then have 99 users waiting, which have no impact on the current user. You can do these independent tasks all at the same time and get a huge, huge performance uptick.